Hello, I'm John Craddock, and I'm going to be speaking about going passwordless with FIDO2 and Azure AD. I'm a Microsoft MVP and an identity specialist, and I do consultancy around the world, and I also run a couple of masterclasses around the world on identity and troubleshooting protocols. So when we're allowed out again, I'd love you to see you at one of those events. Okay, Joe, if you need to get hold of me, you can get me on Twitter. There's my Twitter handle, and there's even a QR code for you as well. So what am I going to cover? I'm going to start off by looking at why passwords are a problem. Now, I'm sure a lot of us already know that they are a problem, but what I want to do is just set the scene so that when we look at FIDO2, I can show you how FIDO2 eliminates those particular problems. I'm going to start by looking at going passwordless in a fairly simplistic way, and then we'll drill down to FIDO2 under the hood. And finally, we'll see how FIDO2, Windows 10, and Azure AD sign-in works. But as we go through, we'll be using Windows 10 to set up our security keys. We'll also have to set up a policy within Azure AD. So again, we can use those FIDO2 keys. So if we look at passwords, passwords are a problem, number one, because they're a shared secret. So somebody has to create a password, and if we leave it down to the user, we normally get a pretty predictable password. And then that password is shared with a relying party, and we trust that relying party to keep our passwords safe. But let's just drop back to the password, the first off. And what we've got is our user creating it, and say passwords tend to be fairly simple. They tend to be very predictable. So what could we have as a password today? Well, maybe COVID 2020, or maybe awfully bad password be COVID-19, but you never know, that's probably being used already. Problem is with simplistic passwords, they make the account very susceptible to spray attacks. And a spray attack is where we take a predictable password and we simply spray it across accounts. They're quite hard to detect spray attacks, but they're very successful for low-hanging fruit. So people using simplistic passwords, we've got them. And in the last 4 months, there was something like 700,000 spray attacks that were detected. The other way is a brute force attack. And with a brute force attack, what we're doing is we're playing a series of passwords against a single account. Spray attacks across multiple accounts, brute force attack against a single account. Much easier to detect. And also, it's much easier to prevent. So, bad passwords, very simple to pick low-hanging fruit against the user. But of course, what we're doing is we're sharing that secret. So our user has shared the secret with the relying party. Now, what is a relying party? Well, the relying party could be a website, or it could be an IDP that actually does identity for multiple websites. And a typical example of an IDP would be Azure AD. So we have one set of credentials which allows a single sign-on to multiple websites. Now, with a website, the security may not be very good around the website. And of course, breach attacks are very, very common. And if you have a look at the website, Have I Been Pwned? It's currently reporting 438 pwned websites with something over 9 billion pwned accounts. And of course, as soon as those accounts have been pwned, what's happened is that that information has been published on the dark web, and then immediately what starts to happen is that credential stuffing is used as a way of attacking, because many people are using the same password on multiple sites, but lots of people use the same username and passwords across multiple sites. So it's referred to as credential stuffing or breach attacks. Another thing, people get emails, and when they don't get emails, they get very disturbed. You've received something like this. This looks really genuine. And, organization, XDS Hub, undelivered emails. And it says multiple emails are pending delivery. Click here. So I click here, and I end up at what looks like my corporate logon. and it all looks amazingly genuine. And remember, I'm a little bit savvy with security, so I check my address bar, log microsoftonline.com. That looks good, and it's HTTPS, and the padlock's there, so the certificate must be good. Of course, I haven't really looked at that in a lot of detail. And the thing is, it's so easy to come up with a website that looks like a genuine site. And this particular DNS name, a few weeks ago, I could have bought for 99p. And I could have set that up. I could have screen scraped your corporate logon and presented you with a logon screen. You log into this, and immediately I've got your username and your password. So phishing attacks are very easy or very easily used to grab credentials. And then, of course, password resets. Password resets quite often done against a compromised email alias. So a hacker has already compromised an email alias. They go and do a password reset. The reset email is sent to the compromised email alias. And again, they've got you. The other thing is you might do a password reset via knowledge-based authentication. You've got KBA security questions and answers, and quite often people give away their information via social media disclosure. So our challenges is, number one, is educating users about password security. It's really, really difficult. And it's really difficult to get users to consistently think about password security. MFA is an absolute must. MFA will eliminate 99.9% of sign-ins with compromised passwords succeeding. Now, in most cases, simple SMS MFA will be sufficient. But for convenience, because MFA via text message is not particularly convenient. So for convenience or high value accounts, go for alternatives. Go for things like using an authenticator app. If you're using an authenticator app, SIM hijacking is not going to, you won't be compromised through SIM hijacking because it's also bound to the device as well. But one of the key things to do is not to prompt or over prompt for MFA. If you over prompt for MFA, and I've seen some companies do this, what's happening is the user's continuously being prompted, probably on their authenticator app, and they simply look at the notifications and go accept. And before you know it, they're looking at the notifications and going accept every time they're prompted, regardless of whether they're actually logging in or not, because they could be working on their machine and they think, oh, it's Outlook prompting me again to sign in. So what I'm going to do is just go accept. And before you know it, they're on the beach and they just go accept. So actually, over prompting is a really, really bad thing to do. So keep your MFA sensible. But if passwords are such a problem, how can we eliminate them being a problem? How can we get away from them being compromised? And the answer is we want to eliminate shared secrets. So Azure AD passwordless sign-in does a really good job of this. So what happens is when you go to sign in, if you've set up Azure AD to do passwordless sign-in, it will pop you up a message saying approve the sign-in, and there will be a number there. And what will happen is on your authenticator app on your phone, you will need to select that a number. You'll be given a choice of 3. And by selecting that number, the users involved, number one, it proved they've seen the sign-in request screen. Because if you're being prompted the authenticator app and you're just doing MFA, you may approve it without actually seeing the sign-in. And somebody could be signing in somewhere else and you've just approved them. With this, by actually selecting the number that's shown on the sign-in, you've made that link. So you've got a lot more security through doing this. But of course, this is a Azure AD Pacific solution. And what we want is something that will scale across the whole of the internet. Back in 2012, the first Identity Online Alliance was founded, and their mission was to work on creating a passwordless authentication protocol. So it's been thought of for a very long time. In 2014, the Alliance actually published two protocols. One was the FIDO Universal Authentication Framework, which is referred to as FIDO UAF. And the other one was the FIDO Universal Two-Factor, FIDO U2F. So the first one, the UAF, was a passwordless protocol. The U2F was to give you second factor authentication. U2F became quite popular and it was used by Google. UAF didn't get a lot of traction. But in 2019, the FIDO2 core protocols were published. And one web authentication protocol, or WebAuthN, has been adopted by the World Wide Web Consortium as an internet standard. And as soon as we've got it adopted as a standard, it means that we can actually do FIDO2 authentication across the complete web, standards-based. In 2019, Microsoft Hello got certified as being FIDO2 compliant. So that is completely FIDO2 compliant now. And it also opened the floodgates for many vendors to release FIDO2 keys. And absolute proliferation of keys. If you've attended any major events in the sort of last part of last year, you would have probably been able to get your hands on free giveaways of FIDO2 keys. They come in different form factors. So some of them are USB, some of them are USB-C. There's ones that are actually also near field communication and Bluetooth as well. So what do? We replace shared secrets with asymmetric cryptography. So we have our user at the browser and the relying party. And remember, the relying party is either a website or it's an identity provider of some kind. So with our browser on the user's system, what we have is a secure store. And in that secure store, we identify relying parties. And when we identify a relying party, and we'll identify them first when we register with them, when we do that initial registration process, we'll have a relying party identifier and then a private key and a public key. The private key never leaves our secure store. We go through a registration process, and during that registration process, what we'll do is we'll register our public key with the relying party. And the relying party will sort of hold that public key against a user identifier. And that user identifier can be unique for every single relying party. The public key is always unique. The user identifier can be as well. So what this allows us to do is send a signed message from our browser to the relying party. The relying party received the signed message. What was it signed with? It was signed with a private key that never leaves the user's possession. It arrives at the relying party, and what the relying party could do is, using the public key, it can verify the signature. And in verifying the signature, it proves two things. Number one, it proves that message has come from the person that holds the private key. That was the person that registered in the first place. So we've proved that the same person is coming back. By verifying the signature, we can also check that the message has not been tampered with. So what we've got is proof that this message has come from the original registrant, and secondly, that it has not been tampered with. And that's all we can prove, but that in itself is quite a lot. So a lot of people ask me about the crypto signing process, and I thought I'd just include a slide on this. So what we have is the signer of a message, and we have the verifier. And what we'll have is the signed message itself, which consists of the original message and a signature. So what the signer does is they take their message, they put it in the package ready to be transported. They then take a hash of the message. They pass the message through a hashing function. And what a hashing function does is it comes up with a fixed length hash. Regardless of the size of the message, the hash will always be of a fixed length. And the very clever thing about hashing functions is that it is highly unlikely that two messages will actually result in the same hash value. It's not impossible, but for all practical purposes, you can consider it to be impossible. So we've got the message, pass it through a hashing function. We've now got a fixed length hash. We take that fixed length hash and we encrypt it. We encrypt it with the private key of the user. That then becomes the signature, which is now transported to the verifier. The verifier takes the message and pushes it through exactly the same hashing function, and we end up with a hash. If the hash on the right-hand side matches the hash on the left-hand side, then it is proof that the message has not been tampered with, right? Because it has to be the same message, because otherwise the values would not be the same. But how can the verifier prove that? Because it can't go back to the signer and say, is it the same hash? So what the verifier does is takes the signature, decrypts it with the user's public key, and having decrypted it, has now got back the hash that the signer put into the message. And if the ones that the verifier has computated and the one that the signer sent, if they match, then it proves two things. It proves, number one, the sender of the message has the private key, which is associated with the public key, and also that the message has not been tampered with. So if we look at FIDO2 authentication, what happens now is we start an authentication sequence. So we initiate authentication, and then what happens is we send back a challenge, and the challenge is passed to an authenticator. So this is not done in the browser. It's passed to an authenticator, which could be a platform authenticator, or it could be a roaming authenticator, such as a FIDO2 key. Having got to the authenticator, the next thing that the user is going to have to do is verify themselves to the authenticator. And they can either do that through a biometric or through a PIN. Having done that, they've unlocked the authenticator's access to the public-private key pairs. So the next thing that happens is the appropriate private key is found and the challenge is signed and sent back. We then receive the response, and what we can do is we can take the public key, because we know the public key associated with that particular user, and we can verify the response. And if the signature is valid, it means the user that sent this message has the private key, is in possession of the private key, and the message has not been tampered with. And by the way, this signed response is referred to as an assertion, which is not to be confused with an attestation, which I will come to shortly. So the signed response is an assertion. So if you want to set up a FIDO2 security key with Windows 10, it's very, very easy. You can go to the security key settings. You can set a PIN. You can then go and set a biometric on it if it is a key that supports a biometric. And you can also reset it. One thing to be aware of, though, is when you go to reset a key, you might find you get a rather obscure message, could not complete a security key reset. If you see that message, it's likely that you need to remove the key, plug it in, and do the reset within 10 seconds. Because you have to reset within 10 seconds of powering up the key. So if you see the message, don't worry about it. Just remove the key, plug the key back in, and then start the reset sequence again. To enable FIDO2 to be used in Azure AD, what we have to do is go to the authentication method policy. Currently, there are two policies presented, FIDO2 security key policies and Microsoft Authenticator passwordless sign-in. But in the future, this probably will be the place where we do MFA, we do self-service password reset, and probably we set up a password policy where we could disable passwords within Azure AD. So we need to go and set this up. And what you can do is you can enable it. You don't have to enable it for all people. You can enable it for a targeted set of users and so on. Right, let's get in under the hood. So let's see a little bit more detail of what's going on. So if we look at the FIDO2 components, we have the client platform where the browser is going to be, and we have the relying party where the server app is. Sitting inside the browser is going to be some client-side JavaScript, which has been served by the app. And we're going to do the authentication between the browser and the server app. And that's going to be using the WebAuthn protocol. Now, the browser is not capable of signing anything or anything else. So what it needs to do is it needs to talk to WebAuthn APIs. And those are supported in most modern browsers. Again, the APIs need to call out to an authenticator. And they can call out to a roaming authenticator. And that roaming authenticator could be a FIDO2 key, and it could be a FIDO2 key that is supported by USB, supported by Bluetooth Lite, or supported by through near-field communication. And to talk to the key, it uses a protocol called CTAP. And if you're talking to a FIDO2 key, that is CTAP2, and CTAP stands for Client to Authenticator Protocol. We can also support CTAP1. And in this scenario, using WebAuthn, we can actually do two-factor authentication. That's using the U2F standard. And there are lots and lots of U2F keys out there. So rather than just making them redundant, saying you have to throw those all away, you can still use them if you just want to do two-factor authentication. But we're talking about FIDO2 here, so we need to be using CTAP2. But we don't have to have a roaming authenticator. We can have a platform or a bound authenticator, in which case you'll be talking to the platform authentication APIs, and that platform authenticator will be a TPM. Or you can also do all of this in software, but you probably, for security reasons, certainly want to use a roaming authenticator or a platform authenticator in TPM format. Now, on the server side, what we need to do is have a way of verifying the actual authn flow, and for that we're going to be talking some library APIs, and we need a user with the user IDs in there and a public key store. So we'll need access to that. And then what we'll have is attestation verification, and we could be verifying the attestation data against the store that we hold, or we could be calling out to an external metadata service. Now, what an attestation allows us to do is pass details of the roaming authenticator or the platform authenticator and verify it. And as a server app, we can say, hey, you know what? I don't really care what type of authenticator you're using. I will accept it. As long as you handle WebAuthn correctly and sign things and pass information back, that's fine. Or you could be a bank and you say, you know, if you're going to do this, I want you to use a particular authenticator. I'll come back to attestation data in a little bit more detail in a second. So that's the main components. Now, on the server side, that could be an IDP. And of course, when we're doing it in Azure AD, it is Azure AD that we're talking to. But you could deploy a website in Azure AD, and rather than using the Azure AD authentication, you could implement your own FIDO2 authentication if that's what you wanted to do. Now, there are two ceremonies, and the first thing is registration. This is where we pass the public key to the relying party. And then there's the authentication ceremony. And during the authentication ceremony, we're using WebAuthn to actually authenticate the user against the relying party. So let's start off with the registration ceremony. So the first thing that happens is the client will talk to the relying party and say, hey, I want to do a registration. And the relying party will send back a create credential command. And that's fairly complex. There's a number of components, and this gives us the real power to the system. So number one, we send back a challenge, and we always send back a challenge. A challenge is just a random string of bytes, and what the client can do is it can sign that challenge and send the challenge back. And then the person that sent the challenge in the first place, the relying party, can actually verify it. And it can be used for prevention of replay attacks. The one very, very important thing that the relying party will do is send a relying party identifier. And that will be on the form, let's say a domain name. So let's say I'm using xtshub.com. I will send that as a relying party identifier. We then send information about the user. This is a randomly generated ID, and it's just going to be used for associating the credential with a particular user. We'll then specify the public key parameters that we can use, the type of crypto public keys that are acceptable to the relying party. And then we can specify the authenticator. And we can say we want you to use a cross-platform authenticator or a roaming authenticator, such as a FIDO2 key. We're not saying it has to be a near-field communication or it has to be Bluetooth. We're just saying cross-platform, or we can say a platform authenticator, and it's also referred to as a bound authenticator. So that's a TPM. You can also specify if the authenticator private key should be residential. That's required when we go passwordless authentication and also nameless. However, if we're using two-factor, what we do is we log in to our relying party using a username and password. Now, when we do the initial registration for the second factor, what can happen is the authenticator can generate the private key. It can then wrap it by encrypting it again with a private key that is just known to the authenticator. It can then pass back that wrapped private key to the relying party. Right? So when you log in again using your username and password, that wrapped key can be passed back to the client side. The advantage of using wrapped keys is that we do not need any storage within the authenticator itself. But as I say, if we're doing FIDO2 and we're doing nameless and passwordless, absolutely 100% we need to actually have the keys residential. The next thing is we can say if we want users to be verified or we discourage users being verified. And by verified, we mean actually verified to the authenticator, either through a biometric or through a PIN. Now, if you were doing two-factor, you may not want that. But what you will want is the user to show presence, to show that they're actually there. And so they use a gesture and maybe touch the authenticator key just to prove they're there. But they're not actually being verified that it is that particular person. To verify them, you'd have to do it through a biometric or you'd have to do it through a PIN. Timeout is just, when to give up and throw an error. And then attestation. Does the replying party actually require attestation data? And this is where a relying party may be saying, I don't care what sort of authenticator you use, or some security officer has said within your organization, you can only use this particular make of FIDO2 key. And then you actually want the attestation data back so you know the type of key that's being used. So registration ceremony, a bit more detail. Create credential. And the first thing we do is we validate that relying party identifier, xtshub.com. And what the client will do is saying, hang on, I am connected to xtshub.com. Great, that's valid. So the client checks the origin that it's connected to. But if you've got a man-in-the-middle attack and we've persuaded you to come to XTS hubs with an S.com, and where this is a man-in-the-middle attack going on, and then the man-in-the-middle is relaying to the genuine site, which is xtshub.com, what will happen is the client will say, hang on a minute, my origin is xtshubs with an S.com. The relying party is xtshub.com, and it immediately rejects it. So this has completely eliminated man-in-the-middle attack. All right, so we've got rid of that issue, so phishing through man-in-the-middle attack. Next thing, the client will pass on all the information to the authenticator. The authenticator will want the user to verify, so that we're doing verification and we're doing FIDO2. And then what happens is it generates a key pair. It will also generate a credential ID. And then what it will do is it will securely store the private key with a relying party ID and the credential ID as well. That stored never, ever leaves the authenticator. And then what we do is we build and sign a response. There's no point in signing it with our private key because the relying party at this stage doesn't know what the public key is. But what we do is we sign it with the attestation private key, which is burnt into the device. It's not a unique key per device, because if it was, we could be tracked across the internet by looking at that signing key. What it is, it's a unique key for a model of devices. So in particular, so if we got the Hoochie Coochie 2000 authenticator model 568, then it will be the same key across the model 568. So it'll be thousands of devices that have this same key burnt into them. And that's the attestation private key. That message goes back to the relying party, and then we verify the origin. So it's making sure that we're happy there's no man in the middle. We verify the challenge has been sent back correctly. We can verify the attestation signature, because what we can do is we can check and get the public key for the attestation. And then we can verify the attestation root trust all the way up to root. We then store the user ID, the credential ID, and the public key. Attestation metadata, as I say, the FIDO Alliance metadata service, they have a metadata service where a vendor can register metadata statements, and it provides characteristics and capability of a particular authenticator. It can even have an image of the authenticator, and it allows you to make risk-based decisions as to whether you're going to use a particular authenticator. And the authenticators are identified by an AA GUID, or an authenticator attestation GUID. Okay, identifying the user. Now, this is an interesting one. We started off not identifying the user at all. All we did is we registered a public key. And all we can tell, the relying party can say it's the same person coming back. And that's referred to as trust on first use. So it assures the user registering the credential can then authenticate against the relying party. And we know always that it's the same user. But we could go through an invitation process. So I could send you an invitation with a code in it. And when you come to register, you supply that code. And that code could be sent via email. It could be sent via post. So it actually checks your actual address as well. We could do full identity proofing. So a user needs to turn up with documents and provide their own presence to actually get something registered. Or we could bind to an existing credential. And this is what Azure AD does. When we register with Azure AD, a FIDO2 device, what we're going to do is have to sign in with strong authentication to actually register the credential and our authenticator. We can also, very important, we can't back up the keys from an authenticator. So what we do is we register multiple authenticators as our backup recovery plan. So when it comes to authentication, relying party sends off a challenge, And again, we check that there's no man in the middle by checking the RP ID and rejecting if the RPA ID and the origin are not matching. We then send the information through to the authenticator. The user verifies against the authenticator. And then having done that, we retrieve the private key using the credential ID. And then we can also verify the credentials created for the particular relying party. And then we can build and sign the response, which gets sent back and can be verified by the relying party. And that completes the whole cycle. So we've registered and we've authenticated. What I'd like to do is just do a very quick demo of actually going through this. I'm going to be using a website. These, by the way, I've got links to these websites in the slide deck, so don't worry about writing them down. What it is, it's WebAuthn.io. It's sponsored by Duo. And I'm just going to use, just to show that this is all very generic, I'm going to create a user, John1, and I'm going to register that user. And what it's doing, first of all, it's saying, hey, Windows, hello, shall I create you a credential and register for you? I can do that because hello is actually FIDO2 compatible, but I can cancel that. And then it's saying, do it through your security key. And it's saying touch your security key, but it actually means verify against your key. So I'm going to use a biometric. And what I've done is I've touched the key, it's read my fingerprint, and I've now successfully registered. I can now log in. And again, I'm being prompted to touch my key. So I'm verifying against the key with the biometric, and I've successfully logged in. And that takes you through the process. So I got credentials for John. Let's try again, and let's do it a slightly different way. What I want to do is to go to some advanced settings here. And I'm going to, in the advanced settings, make some changes to that initial request for registration. So I'm going to have a new user, and it's going to be John2 in here. And I'm going to say attestation type. Well, currently it's none. I'm going to go direct. I want an attestation. And then I'm going to say, let's use a cross-platform device. And I'm going to say register with resident keys. I go to the registration process and things will change slightly. So number one, it's asking me to if I want to actually store details in the key. I then sign in and it's saying, do I want to pass information to the website? And I've said yes. And the reason I'm being prompted with those two things was that I got prompted because number one, I said store residential keys. And number two, I said pass attestation data. Now, in terms of the attestation data, I can allow or block keys using the AA GUID. So I use the AA GUID for a particular key model, and I can allow it or I can block it in Azure AD. So in terms of blocking security keys, if I block it during registration, it tells me that it's blocked by my organization. If after registration, I make a change and block it at sign in, it will tell me your company policy requires you that you use a different method to sign in. Now, what about Windows 10 sign in with FIDO2? Well, it's if you're going from one to one, Windows Hello for Business is the recommended way of doing it. If you're going from one to many devices, then you can use a FIDO2 security key. And what will happen is you will be prompted to insert your key and then asked to touch your key. And remember, you have to verify against the key. So if it's not a biometric key or it can't read your fingerprint, you will be prompted for a PIN. If you want to go SSO on-prem, then in terms of SSO on-prem, what we've got is when we authenticate against Azure AD, if we're using a username and password, what we end up getting back is a primary refresh token. A primary refresh token will give you single sign-on against all Azure AD authenticated resources. But if you want to go against on-prem, so we can use a username and password to get a Kerberos TGT. And that key Kerberos TGT will give you single sign-on against all on-prem protected resources via Kerberos. But if we use a FIDO2 key, what we get back is a PRT. But we've got no username and password to actually get our hands on a TGT. So we cannot get a TGT for access to on-prem. But there's a solution for that. And this is in preview at the moment. And there's a number of things we need. Number one, we need the latest Windows 10 version. We need the latest build of Azure AD Connect. And if you're not familiar with Azure AD Connect, it synchronizes users from on-prem into Azure AD. What that will allow us to do is using PowerShell is create a dummy RODC in our on-prem AD. And that's it's created by Azure AD Connect. However, this doesn't exist as an RODC. It's purely an object in our directory. And associated with that will be a KRB TGT account, and there will be a domain and a key associated with it. That key is synchronized or taken up into the cloud. It's double encrypted during the transfer, and having transferred it up into the cloud, it's then re-encrypted with an Evo key. So we actually have the encrypted RODC key up in the cloud. The next thing is we need some domain controllers, either 2016 or 2019, and they need a patch. And then we're ready to go. So now we sign in with FIDO2, and at the same time as getting a PRT back, we get a partial Kerberos TGT. And that Kerberos TGT has no authorization data in it at all. But what the client can do is it can swap it now for an on-prem full-blown TGT. And with that, we've now got single sign-on against on-prem devices. So anything protected with Kerberos, we got single sign-on for. And actually, it also supports, we can manage NTLM as well. Okay, so we can live in a world without passwords. So let's have a look. A user is required to create a password. No more. We have unique cryptographic keys generated, and they're generated for each site. So never is something used across two sites. The user reveals their password through phishing attacks. Well, I mean, in theory, you could give away your PIN via social engineering if you were using a device that used a PIN rather than the biometric. However, you're not going to succeed without an authenticator. So they've either got to get hold of your device or they've got to get hold of your FIDO2 key and your PIN. And remember, all credentials are scoped to a particular relying party. So it eliminates man-in-the-middle phishing attacks, sort of fake websites trying to phish credentials. The targeted system holds a database of usernames, password, and possibly KB answers and questions. It doesn't matter. You can now steal. You can do a breach attack against the target system, the relying party, steal everything, and it is totally useless to that hacker because all they're going to get is a unique user ID, and they're going to get a public key, and there's absolutely no benefit to the hacker whatsoever. So we've eliminated all of the challenges of passwords. If you want to play, I've put some URLs of websites up there, which have some demo, code for using FIDO2. One thing I would recommend is don't put your FIDO2 keys into Windows Hello. If you do, it's very challenging to actually clear them at the moment. That will change, but at the moment, it's very, very difficult to clear them down. I've got a blog as well that you can look at. And if you once we all get allowed freedom again, please join me for a masterclass. They're sort of all around the world, and I'd love to see you there. Great. Well, thank you very much for joining me. A bit of a whistle-stop tour, but I hope it's explained a little bit about how FIDO2 actually works under the hood. It's quite a mysterious topic, so that should help. You can also see how it can be used for eliminating passwords. Remember, it is internet scalable. It can be used directly on a website, but it's now built into Azure AD. Azure AD can leverage it, and also Windows 10. So I encourage you to take a look at FIDO2 and its implementation in the Windows and the Azure ecosystems. Thanks a lot.